Hello everyone and welcome back to the Kohi Game Engine series. Today we are going to tackle specular reflections. So before we jump into the video, I'd like to thank a few special people. We have the partners of the channel. Those are the highest tier of support through Patreon or YouTube memberships. And those partners are Caden, Eearslya, Joel, Kyla, and Wensheng. Also supporting the channel are all these other fine people on the screen. Thank you all very much for your support. It is greatly appreciated. If you'd like to support the channel and support my work, feel free to have a look at the YouTube membership, or if you prefer Patreon, you can check out patreon.com/TravisVroman. So up to this point, we've already covered a basic directional light and diffuse lighting. So our normal diffuse lighting is basically this portion here where we have a light, in this case the sun, that comes from a direction and reflects the color of that sunlight off of the surface around the normal vector, which comes directly off the surface. So a specular highlight is typically found on shinier surfaces, although somewhat dull surfaces can have it too. And basically the way this works is you have a difference in texture on the surface, and the difference in that texture defines how that light reflects off of it. So what that means is you have a certain amount of light that reflects off the surface and a certain amount of light that sort of bounces around on the surface and is sort of absorbed by the surface. And so the more light is absorbed by the surface, generally gives it a dull finish, whereas more light that reflects off of it typically gives a shinier finish. So if you think about a sort of rubber surface as compared to a, say, metallic surface, there's a big difference in the amount of light that reflects off of both of those. And a specular highlight is one of the effects that we use to simulate that reflectiveness of surface. And so we have various properties that we can use to determine how much of that light gets reflected. But the important part that we're going to focus on for the moment is how that reflection is actually calculated. So we have our color reflection for our diffuse here, which is basically you have your light hitting the surface, and then you take that angle and you reflect it the other direction around the normal, and that is what sends out the color that eventually our eye picks up. But to get the reflection amount, that is actually based off of the view angle and the reflection angle. And it's basically a halfway angle in between that. So wherever this reflection angle is and our view angle, that is where the specular highlight is going to appear on the surface. The other thing we have to keep in mind is we have surfaces that can reflect different amounts of light from different portions of it. So let's say we have a texture that has both a wood texture on it and a nail texture on it. Well, the nail head that's on the top of that wood would reflect more light than the wood portion itself. And so we want to be able to control this thing with another texture. And that texture is going to be what we're going to call a specular map. And so we're going to be adding another sampler to our shader to accept a specular map. A specular map simply works along with our diffuse color to determine how much reflectiveness should occur at that point in the texture. So under assets, I've added some new textures under here, and I've actually added a specular map for each one of these textures. So we have our example textures of cobblestone and our paving material and our paving 2 material. And then also our orange lines, which is what we're using for our cube at the moment. I've gone ahead and added a specular map to that too. I've also gone ahead and added normal maps just as a preview of what's to come, but I'm not going to go into those for right now. Those will be on the next video. So our specular map for a given texture, let's say we have this cobblestone, for example. A specular map might look something like this, and the whiter the surface is, the more that portion of the surface actually reflects light. Now, these are not 100% accurate because they are auto-generated. However, these do give us a clear indication of which parts of the texture is going to reflect and which part is not going to reflect as much light. So we have a couple of examples in here of that for each of our individual textures. Again, the white portions of the map will reflect more than the dark portions. So what we'll have in this case is these stones will actually reflect more than the space in between the stones. So if we just compare those two, we can kind of see how they overlap and how they'll be used. So I've gone ahead and added those, and then I've added one for our 512 texture as well. And basically what this is going to do is it's going to take the black parts of the texture. So if we take a look at this, our black parts of the texture here are going to be the parts that are going to be shiny, and the orange parts are going to be the parts that are not shiny. So just so you guys kind of understand how this is all going to come together. I think probably the best place to start is with our material configuration changes. So in our test material, we have a new property that is called shininess, and that determines how shiny the surface is overall. So a higher number here indicates more shininess, a lower number indicates a more dull surface. So the higher this number is, the more tightly concentrated the light reflection of it is going to be. The lower the number, the more sort of spread out that number is going to be. So 64 is pretty shiny, and I'm using this exaggerated value just to sort of indicate a little bit more clearly as to what the difference actually is. The other difference is we are adding a new map. We're going to call that Specular Map, and we're just going to point that to the specular texture for the orange lines 512_spec. So the next set of changes I'm going to point out is actually in the shader. So I figure we'll tackle the sort of configuration of this first, and then the shaders themselves afterwards. So we'll take a look at the shader config itself. And this has a couple of things added to it. So the first one is we have our sampler here. This is a instance sampler, and it's called Specular Texture. So it just comes directly after our diffuse texture. And then we have another one here that is a F32 that is shininess. So that's just a float number that gets passed in. So we have those added there. And if we take a look at our vertex shader, we have a couple of changes here as well. So one of the first things that we're going to add is the view position, because unlike before, we actually need to know where the camera is in relation to the current fragment that we are looking at. So we need to take the view position in, or the camera position, if you will, so that we can use that to calculate the light reflection. Since we are taking that in, all we are going to do with it is pass it over to the fragment shader. So we are just going to add that to our DTO here. And we're going to also add the fragment position, which is the three-dimensional coordinate in space of the fragment that we're going to be generating. So that is basically just our in position that is passed in times our model matrix, and we just copy that over. So we have that and our view position, which is copied over here as is. Next, we have our changes to our fragment shader. So there are a couple changes here that we should note. The first is in our local uniform object, we have our object UBO, we have our shininess. So we now have our diffuse color and our shininess. And a little bit further down where we handle our samplers, before we just had a diffuse, now we actually have two. And the way our setup is configured, these textures will actually be coming in as an array of sampler 2D. So we have, instead of just a single sampler here, we have an array of two. And then I've defined some constants here as to what each index of that is. So the first index is going to be our diffuse sampler, and the second is going to be our specular sampler. And so this just makes it a little bit clearer when we're referencing these indices in code as to which one we're actually doing, because 0, 1, and eventually 2 and others are not quite as clear when you're examining the shader code. It's much more helpful to have named constants. So as we added in our DTO on the other side, we have our view position and our fragment position. Again, those have to be in the same order as they are on the other side. When we calculate our directional light, we have added a new parameter to this. So that is view direction. That is where we're going to use this view position and fragment position. So the view direction is calculated by taking the view position and subtracting the fragment position from that. So that gets our direction from the camera or the view position to the surface that we're actually looking at. And we go ahead and pass that to our calculate directional light. So our calculate directional light just has a couple of changes to it. So we have the half direction, which is what we use to calculate the reflection, and then what we were going to call our specular factor, which is how much the specular highlight actually influences the current fragment that we're rendering. And so that is using the half direction, which is the view direction, and light direction, which is the directional light direction. And we go ahead and get the dot product, so the difference between our half direction and our normal. And then we go ahead and make sure that we don't have any negative values there. And then we go ahead and set that to the power of the shininess. So that is where our shininess factor comes in. One quick update here as well. Our diffuse sampler is now taking from our samplers array at the index for sample diffuse, which is 0. And a little bit further down, we apply our specular by taking a sample of the specular sample. So that is the samplers array at the samp specular index. And we go ahead and use the same texture coordinates. We take the RGB of that, and then we use the alpha of the diffuse. And the reason for that is because we don't want to be reflecting light in an empty space on the texture, so like between tree leaves or something like that. So if that alpha is 0, that's obviously going to zero this entire thing out, meaning it shouldn't render in the first place. So that is how we calculate our specular, and then similar to how we treated our ambient and diffuse, we just add in the specular amount to that. So all this light is additive up to this point. So all we do is we return our ambient, diffuse, and specular added together, and that is our final light color. And that is it as far as the shader updates are concerned. One more thing that I would like to point out is for consistency purposes, since we've started using an array of samplers here, in our UI shader, I've gone ahead and converted this to be an array as well, just to make it the same. Because technically speaking, we've gotten away with it because it was only an array of 1, but we really should be treating this as an array. So this is just sort of a little bug fix that I've implemented here. And for right now, it's just an array of 1, but we've gone ahead and properly indexed that. Okay. So one other change that we've made is we have this view position that we use, but we actually need somewhere to be able to store and update that. And if you recall, all the way back in our game, we are actually recalculating the view matrix and then calling this renderer set view. And this hack still exists for now because we don't have a proper camera system. So we are just going to extend this hack a little bit for now. And we are going to start passing the camera position, which we already had in our state, along with the view matrix. And that's going to give us our view position. So that is going to be exposed in the renderer front end. So in the H file, we have our renderer set view. We are just adding view position to that, which is a vector 3. That's just the camera position. And all we do here is we take that view position and we store it in the state. We store it in the state pointer in a new vector 3 that we have available. That is vector 3 view position. Okay, so we just copy that over. Of course, if we take a look at the front end structure, we now have something here for view position. So we're just going to keep an eye on that view position, or keep track of it as we go. That way we can use that in our shader as needed. This also means in our material system we have an update. Our material system apply global, in addition to projection view in ambient color, now takes in a pointer to view position. So we go ahead and we pass that in here. And that is only passed in for our material shader. So if we go down a little bit further to our UI, we just pass 0 for that because we don't actually need it. So by extension, that means this was updated as well to take in the view position, and that simply looks at our shader and applies it to the view position. This is all code that you guys have seen before, so I'm not going to go into great detail on this. We've just added a new index for our view position that is automatically taken in and tracked. Before we move on from our material system, we also need to take a look at the material loader itself, because it also takes into account the new map. So our material loader also takes in the specular name, and the resource data also has a specular map name added to it as well now, and that is looked up the same way as the diffuse is. So it's just a matter of just adding that field there, and then we can go ahead and look that up. In addition to that, we've also added the shininess property for the material loader. So that has gone ahead and read in here as well. If for some reason it has some sort of invalid value or there's nothing found here at all, it defaults to 32. Taking a quick look at our resource types, there is a small change that we have actually needed to make here. Now, we've gone ahead and added the texture map specular, but I see there that we've actually added that as 1. That should be a 2. So that will be fixed by the time this video is released. But this is just the texture map use. Now, again, this texture use is probably something that we may not need, but we might need it in the actual editor itself. I'm not 100% sure, but for now I still want to track it, so I've gone ahead and used that there. If we go down a little bit further, we see our specular map name has been added here, and our shininess has been added here. Our material itself has also received these updates, so we now have a new texture map for the specular map, and we now have a property for the shininess. And that pretty much does it for our resource types. One more thing that I forgot to point out in the material system is we have actually added something here to load material, to load in our specular map. So our specular map, for now, just follows the same exact logic as our diffuse map. If it's been defined, it's gone ahead and used. If it is not, then it is just set to texture use unknown, and the map is not used. We also, of course, have added to our destroy material the releasing of the specular texture map. And in our default material, we go ahead and use the texture system get default specular texture. So we should go ahead and take a look at that real quick. And all that is it just returns the default specular texture. So the default specular texture is actually generated in this create default textures within the texture system. And all this does is creates a 16 by 16 texture, sets all the pixels to black, which means that by default, materials will not have specular highlighting. This just creates a small texture for the default of that, and that is what is used on the default material when it's created. One more thing that has changed in our game.c is, in addition to setting the view, we also have this debug function in here, which outputs the position of the camera anytime you hit the P key on the keyboard. So that is just a quick debug tool to allow us to sort of fly around and know where we are in the world. Okay, so now on to the Vulkan backend implementation of this, and thankfully there's not too much to be done here. So we have a single change in Vulkan types INL. And all we've done here is we've reduced the shader max bindings from 32 to 2 because we are going to use just the 2 bindings, so the global and the instance bindings. And within those bindings, we could just use multiple descriptors, so we're never going to need more than 2 bindings, at least for our default shaders. So I've gone ahead and reduced that to 2, which will just save us quite a bit of memory. And that is all the Vulkan code that we actually need to modify, folks. That is it. Thankfully, because of everything we've done so far and made it configurable, we don't actually have to mess with the Vulkan code. And so that is sort of the point that we wanted to get to. So most of the rest of the logic that has changed all exists in our application C file. So the first change that has been made is we've actually modified our debug event here, which is when we hit the T key, it just changes out the textures. So we're going to be not only changing out the diffuse textures, but we're going to be swapping out the specular textures to match as well. So we've gone ahead and added the specular in there for the cobblestone paving and paving 2. And this basically just goes through and performs the exact same logic as was being done for the diffuse texture. It just goes ahead and does the same exact thing for the specular texture. So the logic hasn't changed there, it's just using the specular instead. Okay, and that should be pretty much the rest of the changes. We still have our rotation code here for our test model. So what I'm going to do, just to be safe, is I'm actually going to run a task and do a post build, just to make sure that our shaders are built successfully. And I'm going to build the application. And we'll go ahead and run. And it doesn't look different at first glance. However, if we bump the camera down a little bit, and we take a look up here at the 512 text as it spins around, we can see that we do have a reflection on the 512. So let me go ahead and actually slow that down so it's a little bit easier to see. So I'm actually going to set this to 0.5 for our rotation speed. And I'll just launch this again. And we'll bump the camera down and look up a little bit because of the direction our light is coming from. And we can see that our 512 text is now reflecting light. And we can see that all of the lines here are reflecting as well. So if we go ahead and change to a little bit more of an obvious texture by hitting T, we can see our specular highlights showing up here. So we can see that the portions of the texture that are white are reflecting more light than the portions of the texture that are darker or black. And if we go ahead and switch a couple more times, we can see that effect with our other textures as well. We can also see that our textures are being acquired and released properly, so we know all that logic works as well. And that is it, folks. That is how you implement specular highlighting in Kohi. So next we're going to be moving on to normal maps, which involves quite a bit more changes to the system, but thankfully not a whole heck of a lot in terms of actual Vulkan code, because most of it is going to be on the engine side itself in configuration. So normal maps are next, and we will combine those with our specular maps to give us a real nice and dynamic looking surface with nice looking lighting. So that is coming up next. Thank you guys so much for watching. If you liked the video, please toss it a thumbs up. If you haven't already, please consider subscribing. Click the little bell icon there to get notifications as to when new videos in this or other series drops. And I will see you guys next time.